doing a combustion analysis practice question, and we used Methotrexate as our example. Methotrexate is an anti-neoplastic, which is just a fancy way of saying that it's an anti-cancer drug. It's also an anti-rheumatic, and it's used to treat rheumatoid arthritis. It is composed of 52.86% carbon, 4.88% hydrogen, 24.66% nitrogen, and 17.6% oxygen by mass. And it has a molar mass of 454.46 grams per mole. Calculate its empirical formula and molecular formula, and make a statement about that as well, and predict how much carbon dioxide, water, and nitrogen would be produced upon its burning. So to solve this, the first thing we'll do is make it easy on ourselves. We'll assume 100 grams of the substance. If you assume 100 grams of the substance, then all these percentages can be turned directly into gram amounts, because a 100 gram sample of something that is 52.86% carbon is going to contain 52.86 grams of carbon. So we list all these quantities as grams, so we turn all the percentages into grams, and we divide by the molar mass of each one of the elements. So carbon has a molar mass of 12, hydrogen has a molar mass of 1, nitrogen has a molar mass of 14, and oxygen of almost 60. We get these numbers, and these numbers represent the mole fraction and the mole proportion of a sample of 100 grams. So in a 100 gram sample of methotrexate, you're going to find 4.4 moles of carbon, 4.8 moles of hydrogen, and so on. What you then do is you divide by the lowest number in this proportion, which happens to be the number of moles of oxygen, in the hopes of getting a whole number ratio. It fails to give us a whole number ratio, so we have to look at the numbers, and by inspection we can probably notice most of the time that if you multiply by some low integer value, you can get whole numbers out of it. And it turns out that if you multiply these ratios by 5, then 4.4 becomes 22, and 1.6 becomes 8. And the other two numbers will stay as whole numbers because they're already whole numbers to begin with. So you get 20, 22, 8, and 5. So we're gonna go ahead and predict that the empirical formula of methotrexate is C20H22N8O5. To double check, we're going to find out what the empirical formula weight of methotrexate with this formula would be. And this is what we're doing over here. And we come up with the number 454.44. The question tells us that the molecular weight, the molecular mass of methotrexate is 454.46. Well, that correlates very nicely with our experimental results. So that tells us that we've hit upon the molecular formula of methotrexate. When the empirical formula weight and the molecular weight are the same, you know that you've hit upon the actual formula. So the empirical formula weight is identical to the molecular weight, which tells us that the molecular formula of methotrexate is correctly predicted here. The next step of the problem, we're asked to find out how much carbon dioxide, water, and nitrogen is going to be produced. So the first step in solving this problem is to balance the combustion equation. So I'll show you how I did it. We start off with an equation, the formula of methotrexate, plenty of oxygen to burn the substance, and then the byproducts that you would get if it was a complete combustion. You would get carbon dioxide, water, and nitrogen gas. And you know, you might not exactly get this combination. Sometimes you might have to do two separate experiments, one to measure the nitrogen and one to measure the CO2 in the water. But suffice it to say that you could set it up so that the combustion analysis would give you the correct proportions that are present in the molecules. You might just have to do two different types of experiments at different temperatures or with different reagents present. At any rate, to balance this complete combustion equation, you do it alphabetically. You start off with carbon, then you do hydrogen, and finally you go to oxygen. The nitrogen you can throw in at the end. So the first thing is carbon. Carbon has, there's 20 carbon atoms in methotrexate, so we expect there's going to be 20 CO2s when you burn it. There's 22 hydrogens, so you'll have 11 waters. Then, if there's 8 nitrogens, you should expect to get 4 diatomic nitrogen atoms. And lastly, we look at the oxygen. There are 40 oxygens over here and 11 oxygens over there, so it's 51 oxygens on the right-hand side. You've already got 5 coming from the molecule itself, so 51 minus 5 gives us 46 oxygen atoms that have to come from the oxygen supply. We're going to get that by putting 23 diatomic oxygen atoms. So here's the balanced equation. One molecule of methotrexate will react with 23 molecules of oxygen to give you 20 molecules of CO2, 11 of water, and 4 of nitrogen. So let's start by finding out how many grams of carbon dioxide is produced. If we assume that we burn a 0.15 gram sample, we're not going to burn 100 grams of methotrexate because it's an expensive drug. So we're going to burn just 0.15 grams. Here's the molar mass of methotrexate. So we get 3.3 times 10 to the minus 4 moles of methotrexate. If our experiment works out correctly, we should get times 20 number of moles of carbon dioxide. See how I set up this conversion factor? Where do I get these numbers? 20 over 1. It's from the balanced equation. 20 carbon dioxide molecules are being formed when every 1 mole of methotrexate is burned. We'll see that the moles of methotrexate will cancel, and we're left with numbers of moles of CO2 produced. Then we multiply by the molar mass of carbon dioxide, which is 44.0098, and we can predict that there will be 2.90528, I guess that's a 1, times 10 to the minus 1 grams. We're only allowed 2 significant figures. There's only 2 significant figures here, so when we report our answer, we're going to have to limit ourselves to writing just 2 numbers. 0.29 grams of CO2 will be produced. That's our prediction. For water, we again start with the same number of moles of methotrexate times the stoichiometry of water to methotrexate, which is 11 to 1. So we get 11 moles of water being produced for every mole of methotrexate burned. That gives us 3.63 times 10 to the minus 3. We multiply by the molar mass of water, which is 18.01528 grams per mole, and we get this number. We're only allowed 2 significant figures, so we're going to limit ourselves to writing 6.5 times 10 to the minus 2 grams of water. That's our final answer. Lastly, the moles of nitrogen. We again start with the number of moles of methotrexate times the moles of nitrogen versus the number of moles of methotrexate burned. We get this number of moles of nitrogen times the molar mass of nitrogen. Remember, nitrogen is diatomic, so it's 2 times 14.0067. We get this amount of grams of nitrogen, and then we put it in the form of 2 significant figures. 3.7 times 10 to the minus 2 grams of nitrogen should come out of this combustion reaction. Any questions?